When you handle a piece of metal or stone, you are interacting with the most fundamental property of a solid, its ability to maintain a rigid mass, shape, and volume. At the atomic scale, this rigidity is an illusion. Constituent atoms are in a state of constant, high-frequency vibration, pushing against one another. This kinetic energy is held in check by the defining characteristic of the solid state. Individual atomic or molecular behaviors are overridden by their collective spatial configuration, a strict, rigid order that keeps them locked in place. In order to understand a material's macroscopic behavior, whether it snaps under pressure, whether it conducts electricity, or bends without breaking, we have to map its three-dimensional geometric grammar. Our investigation begins by defining the fundamental units of 3D space, calculating the physical limits of how atoms pack together, and locating the mathematical voids that enable the creation of high-strength alloys. This hidden geometric order is more than a system of classification. It is the foundational blueprint for every material we engineer today. The smallest repeating unit of a crystal is the unit cell. It acts as a three-dimensional tile that, when repeated infinitely, generates the entire solid structure. We define this cell using 6 lattice parameters. First are the lengths of its 3 intersecting edges, A, B, and C. Next are the 3 angles between those edges, known as alpha, beta, and gamma. When all edge lengths are equal and angles are exactly 90 degrees, we produce the cubic system. Altering these lengths and angles yields 7 distinct axial systems, such as the elongated tetragonal or skewed monoclinic. Atoms always occupy the corners, but they can also sit perfectly centered on the faces, on the edges, or deep within the body of the cell. Combining these results in exactly 14 unique geometric combinations. This specific collection of 14 translational symmetries is known as the Bravais lattices. Every known crystalline material in the universe conforms to one of these specific arrangements. Nature's chemical diversity is contained within these 14 mathematical templates. Moving from wireframes to real matter, we must treat atoms as physical hard spheres that possess volume and cannot overlap. When atoms pack together on a single two-dimensional plane, they will naturally settle into the tightest possible honeycomb formation. This foundational layer naturally produces geometric hollows between the spheres. To add depth, the most stable position for a second layer of atoms is to drop directly into these alternating hollows. The lattice now faces a defining fork in the road. Path 1 places the third layer directly over the first layer, creating an ABA repeating pattern, called hexagonal close packing. Path 2 places the third layer over unoccupied hollows, creating the ABC pattern, or cubic close packing. Regardless of the path, both structures hit an absolute physical limit. Exactly 74. In sodium chloride, the sodium cations are the perfect size to inhabit the octahedral holes of the chlorine lattice. Material engineers exploit these voids to create interstitial alloys, intentionally forcing foreign atoms into these gaps to disrupt and strengthen the overall lattice. This is how we produce steel. Wedging carbon atoms into the octahedral voids of an iron lattice creates a structure far stronger than pure iron. By manipulating just the nothingness inside a crystal, we transform soft elemental metals into high-strength industrial materials. Because the spacing between atoms is roughly 100 picometers, they are impossible to resolve using visible light. Physicists solve this using X-rays, as their wavelengths natively match the picometer scale spacing of the crystal lattice. When an X-ray beam hits an ordered lattice, the atomic planes function as a three-dimensional diffraction grating. As the beam strikes the crystal, part of the light reflects off the first atomic plane. The rest of the beam penetrates to reflect off the second layer. This deeper ray travels a slightly longer physical distance. According to Bragg's law, these two rays will only produce a bright signal if that extra distance perfectly aligns their wave peaks. This constructive interference only occurs at very specific angles. By recording the angles of these bright slashes, scientists can calculate the exact distance between the atomic planes. Bragg's law bridged the gap between theoretical geometry and physical measurement, proving that the Bravais lattices are the literal framework of the solid world. Solid matter is built from the unit cell up, bound by 14 lattices, limited by 74% close packing, and customized through its interstitial voids. This profound geometric understanding has enabled a shift from merely observing natural minerals to actively designing entirely new atomic architectures. Today, we apply X-ray diffraction as a precision tool to reverse engineer elements, assembling specific structures layer by layer. From the doping of semiconductors to the engineering of aerospace alloys, modern technology depends entirely on these precise geometric rules. The macroscopic utility of any material is a direct result of how its microscopic elements are arranged in space. To study solid-state chemistry is to master the physical rules that dictate the potential of our technology.